Okay. In this class we will look at linear vector spaces, or you generally call it as LVS. So a linear vector space is denoted by fat V, okay, and is a set a linear vector space. A linear vector space is a set of vectors phi, psi, chi, etc., called ket vectors with an operation called addition satisfying the following properties. Okay, the first one. Okay, so if say V phi plus psi is equal to okay, phi plus psi is equal to psi plus phi, which should be a member. That means for all phi and psi belong to V. So if this means that this first property, which is called the closure property, this is known as closure property, which says that if say phi and psi are elements of the vector space, then phi plus psi must also be a member of the vector space. Phi plus psi, which is equal to psi plus phi itself, it should be a member of the vector space. Okay, so this is the closure property. Okay, I'll repeat that. If phi and psi are members of the vector space, then the phi plus psi should also be a member of the vector space. This property is known as the closure property. And the second property is the associativity. So phi plus psi plus chi, that must be equal to phi plus psi plus chi. This property is known as the, this is the associative property, and you are very familiar with this thing. And the third one is that there exists a unique vector omega such that phi plus omega must be equal to phi for all phi belongs to the vector space. Okay, and this is actually the existence of the identity element. So there should be a vector omega such that if you add omega to any vector, that means phi plus psi, so that should be equivalent to phi itself. So this is the actually the existence of the inverse. Okay, so this is the third property, and the last one okay, this is the existence of inverse. So there is a unique there exists a unique vector minus phi for all phi belongs to V such that phi plus minus phi must be equal to omega. So if for every vector phi, there should be a minus phi such that phi plus that minus phi, that will be if you add phi to that other vector, you will get the null vector, or the omega, you will get omega. Okay. Okay, so these are the under addition, these properties must be satisfied, and then you can say that the set of vectors form a vector space. Or then in addition to the addition of vectors, you can have in vector space you can have multiplication by scalars. So I'll just do that here. Multiplication by scalar. Okay. So, in vector space you can have another operation is multiplication by scalars. Scalar I mean you can have a complex scale is a real scalar or a complex scalar. If the scalar is a real scalar, then the corresponding LVS you call it as real LVS. If we say the scalar which I call it as A, if A belongs to R, okay, then you say that it is a real LVS, or if A belongs to the complex space, then you say that it is complex LVS. Complex LVS. Okay. So, I will just list the properties. Okay. So, if phi is a vector, so A into phi, that should also that should belong to the vector space V for all phi belongs to V. Okay. So, if phi is a member in the vector space, then multiplication by a scalar A into phi, that should also be a member of the vector space, where A can be a real number or a real or a complex scalar, okay, or a real or a complex number basically too. And suppose you have A into B phi, that should be equal to AB into phi for all phi belongs to the vector space. Okay. Now, the third property is that A into psi plus phi, that must be equal to A psi plus A phi for all phi and phi comma psi belongs to V. Okay. And the fourth property is that A plus B into psi is equal to A psi plus B psi, again for all psi belongs to V. Okay. For all psi belongs to V, and then 0 into phi is equal to 0. Okay. So, and okay, so these are the properties of multiplication by scalars. Okay. So, the first one, I mean, so I don't need to explain it further. So, these are all trivial things. Okay. So, all right. Now I'll talk about dual space. For every vector space, the vector space V, there exists a dual space which is denoted by V tilde. Okay, that is also a vector space. This is also a vector space. But the difference is that whose members, I mean, we know that the ket vector is phi, psi, etc. There are the in the vector space V, these phi, psi, etc. they were the members of the vector space. Over here you have the members will be bra vectors, phi, psi, chi, etc. etc. These are the members of the dual space. Okay. So, okay. So, I mean you can regard, I mean for example, I mean to get a feel, you can think if psi, I mean for example the ket vectors, you can regard this as the column vectors. If for example if n is greater than or equal to 2, you can, if you take the ket vectors are the column vectors, the bra vectors are the, I mean you can say that the row vectors. Okay. And okay, so if you for example if you have your psi is say a1, a2, a3, and then the corresponding bra psi that will be a1, a2, a3, the row vector. But I mean, suppose if they are real numbers, a1, a2, a3 are real numbers, bra psi will be just the column the row vector. But on the other side, if they are say complex numbers, then your bra psi must be the complex conjugate transpose. That means if you have a column vector, right, this is a complex column vector, then bra psi will be the complex conjugate transpose. Then you need to take a complex conjugate also. Bra psi, that will be a1 star, a2 star, a3 star. So that will be the bra vector. Okay. So you can just have an analogy like this for the ket and bra vectors. Okay. Or you can say that you can write a for ket vectors you can have a the column vector representation for ket vectors and row vector representation for the bra vectors. Okay. All right. Okay. Now I will talk about inner product. So if you have say two vectors phi and psi, okay. So the inner product of phi and psi is defined by phi psi. Okay, this is the inner product. Okay, these are the inner product, and I mean you can have this following properties for the inner product. Phi psi phi. Okay, the first property is that phi psi plus chi. So I mean your row your here I mean okay. So you can have this is bra phi, then inner product of psi plus chi, that is going to be equal to phi psi plus phi chi. Okay. Similarly, phi plus psi chi, that is equal to phi chi plus psi chi. Okay. And then you can have phi a psi, where a is a complex it's a scalar, where a is a scalar, that is equal to a into phi psi. Okay. Now suppose that you have a phi psi, this is equal to a star phi psi. Okay. And the last property is that phi psi star, that is equal to psi phi. So these are the properties of inner product. All right. Now let's look at. Okay, so I told you, I mean phi psi, if this is the inner product, if it is 0, if phi psi is 0, then you can say that this these are orthogonal, phi and psi and psi are said to be orthogonal. Okay. And now the inner product of phi with itself, phi all raised to half is called the norm of the vector phi. This is denoted, the norm of the vector is denoted by like this. You have you have phi, it should be like this. Okay. So, this is called the norm of the vector, vector phi. Okay. And remember that this is so the norm of the phi is always greater than or equal to 0. Okay. It will be 0 if phi is a null vector. Okay. So, this is the property of the norm. Okay. Norm is always greater than or equal to 0. Okay. It is a real number and it is greater than 0. All right. Now we will talk about basis in vector space, in a linear vector space. Okay. So, suppose you have a set of vectors phi 1, phi 2, etc. Okay. So, if these set of vectors form a basis, if A phi 1, phi 2, say phi n is here, phi n are linearly independent. Okay. And second one, B, if phi 1, phi 2, phi n should span the space. Okay. If these two conditions are met, that means if phi 1, phi 2, etc. up to phi n, they are linearly independent, and then this set phi 1, phi 2, phi n should span the space. Okay. If these two conditions are met, you can say that this set forms a basis. This forms a basis. I will explain you what do you mean by the linearly independent, and then what do you mean by spanning the space. Okay. So, let us take the first case. Okay. I mean, the formal definition is that, I mean, suppose you have this, suppose you have a if a I phi I from I equal to 1 to n, if this is equal to 0. Okay. So, that then if you have a set of vectors phi i's and there is a relation which says that summation I equal to 1 to n a I phi I equal to 0, this will satisfy only if all a i's are 0, all a i's are zeros. Okay. Then you can say that these phi i's are linearly independent, or if phi's are linearly independent, then summation over I equal to 1 to n a I phi I equal to 0, the only solution is that a I must be equal to 0. Okay. This I mean, or it says that in this, I mean, you see that there are n vectors like here, right, and any of this vector you cannot write in terms of the other vectors. Okay. If you take any vector of this set, you cannot write this vector in terms of the other vectors. Okay. That is what for example, I mean, you can see that the unit vector I j k in 3-dimensional Cartesian space, then you know that these I j k are the unit vectors, right, and you know that if these three vectors, I mean, you cannot write I in terms of j and k, or j in terms of phi and k, or k in terms of phi and j. Okay. So, because these vectors are linearly independent. Okay. All right. And so, I mean, the next all right. So, I mean, I can very well ask you, if say I plus j, I minus j and k, are they linearly independent? Of course, they are linearly independent. Okay. So, now let us talk about what do you mean by spanning the space. Okay. So, given an arbitrary vector in the vector space, V, so say given an arbitrary vector, so I mean, this vector should be able to, you should be able to write in terms of I some a I phi I. then you say that this these vectors span the space. Okay. So, I mean, given an arbitrary vector in the vector space, with this vectors, if you can express that arbitrary vector, then you can say that this set span the space. Okay. So, if you are given a set of vectors, and if these vectors are linearly independent and if they span the space, then you can say that this forms a basis. Okay. So, I can say you, I mean, say I already told you ijk, they are linearly independent, and any arbitrary vector A you can write in as axi plus ayj plus azk. So, they span the space. Okay. Any arbitrary vector you will be able to write in terms of the unit vectors I, j and k. So, these I, j, k forms a basis for 3-dimensional Cartesian space. Okay. And now, I mean, you can take the other one, say if you are taking just I and j, you are talking about 3-dimensional Cartesian space, and if you take these two vectors I and j. Okay. So, I and j, of course, they are linearly independent, you can't write I in terms of j or j in terms of I. Okay. So, it is clearly linearly independent. Okay. But will it span the space? No. You need you cannot write any arbitrary vector in terms of just I and j, you need k. So, this ij set, they do not span the space, and the 3D Cartesian space. Okay. And on the other side, say if you take I, j, k and I plus k. Okay. You have I, j, k and I. So, you have 4 vectors, and you clearly these vectors are not linearly independent. Okay. I, j, k, and because I plus k can be written in terms of these 2 vectors. Okay. So, at max you can have in an n-dimensional space, you can have maximum n linearly independent vectors. Okay. Linearly independent vectors. All right. Similarly, we can so, I mean, you say what I am saying is like, so suppose you have a basis, say set phi I forms a basis. So, the number of basis vectors is the dimensionality of the space. This is the dimensionality in the case of Cartesian 3D space. I mean, I, j, k, you have 3 basis vectors. So, the dimensionality is 3. Here the dimensionality is d equal to is 3. Dimensionality is 3. Okay. So, I mean, another point which you note, I mean, so is given a basis, the number of basis vectors will be same, but the choice of the basis vectors will be different. I mean, it is not unique. Okay. So, I mean, for example, I mean, I told you I, j, k, right. So, instead of that I can use I plus j, I minus j and k. This is also a basis. These vectors are linearly independent, and they, of course, they do span the space. So, this is another choice for the, I mean, another basis for a 3-dimensional Cartesian space. So, then you can have many choices, but always the number of basis vectors will be the same. Okay, and that the number of basis vectors gives you the dimensionality of the space. Okay. All right. Now, I will talk about orthonormal basis. So now we have a basis set phi 1, phi 2, etc. up to phi n. Okay. And if the inner product phi I phi j is delta I j, that means phi 1 or if I and j are same, you will get 1, or I and j are different. If I and j are different, then you will get 0. Okay. So phi 1 is 1, phi 1 phi 2 is 0, phi 2 phi 3 is 0, or whereas phi 2 is 1, phi 3 is 1. So this is known as the orthonormality condition. This is the orthonormality. This is not this is the orthonormality. Okay. Okay, this is the orthonormal condition. And now there is another property, is that, I mean, if you have an so suppose you have an orthonormal basis, so you have a basis and that is orthonormal, then you have another property which is called the completeness. Completeness, it says that okay, summation over phi I is identity. This is actually, it is not a this is sort of a matrix identity or an operator identity. Okay. So we will do it. I mean, I'll take an example and then I'll do it. Then you will understand that about the completeness of the orthonormal basis. Okay. And given, suppose now you are given a basis, psi 1, psi 2, etc. up to psi n. This is a basis, but this is not an orthonormal basis. Okay. So so to make an orthonormal basis from a basis is I mean, by you will be able to get an say phi 1, phi 2, phi n is an orthonormal. Suppose this is an orthonormal basis, and this is just a basis. So to become a basis, you need only two conditions to be met, and the first one is there should be the vector should be linearly independent, and the next condition, they should span the space. Okay, but you have if the basis is orthonormal, you need to satisfy this condition as well. Okay, so if you start from a basis to get an orthonormal basis, you can do what's called a procedure which is known as the Schmidt orthonormalization procedure. So I'll explain you what it is.